welcome back to my channel. Today we are going to continue from where we stopped last time. We stopped at the determinant of the matrix. We'll recap and then move forward. So, determinant of a matrix. The general formula is determinant of any matrix A is equal to summation I from 1 to n, where n is the number of. A must be an n by n matrix for us to be talking about determinants. So here this is the n here. Sigma of p. The sigma of p is the sign of the partition. Then A1, P1. P1 is an element in P, the one with the partition, the first element. Then the second element, A2, P2, all to AN, Pn. So an example here, let's just take one example before we leave that. An example here is find the determinant, this is an exercise now, of A, where A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. There are two ways to find these determinants. We can use the formula or use another way. Should we use the formula or should we teach the other way? Formula. We see that A is a 3 by 3 matrix, so n is 3. The partition of this is the partition 1, 2, 3. So we have P is 1, 2, 3, 1, 3, 2. 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So next is to get the sign of the partition. So for the sign of P, we have, considering 1, 2, 3, there's no rotation, so that's 0, which is even, right? So sigma of P will be plus 1. Then 1, 2, 3. I'm going to just swap this and this. I have only one swap.
Yes, going to be now. Wow.
So we have one swap, which will give me what? Negative, right? This is odd, so minus 1. So I have 1, 2, 3. Swap, swap. 1, so it's still negative. Here again, 1, 2, 3. So I'm going to swap 2 here. Take swap 3 and then take 1 here. So I have 1, 2. So that's positive. That's even, so it's positive. Then 1, 2, 3. Oops. 1, 3. So it's also positive, right? 1, 2, 3. 3, 2, 1. It's just 1, so that's negative. Minus 1. I told you that the number of negative ones must be exactly the same number of positive ones. So we have 1, 2, 3 negative. 1, 2, 3 positive. So they're okay. Next is to apply to this formula. Determinant of A is equal to plus, we have A 1, 1, A 2, 2, A n is 3, so 3, P n is 3. So we are going to continue that one. Minus A 1, 1, A 2, 3, A 3, 2, minus A 1, 2, A 2, 1, A 3, 3. I'm here now. Plus A 1, 2, A 2, 3, A 3, 1. I want to number. So plus, we are here now. We have A 1, 3, A 2, 1, A 3, 3. Minus A 1, 3, A 2, 2, A 3, 1. So now, A11 is what? According to this, is A11, A12, A13, A21, A22, A23, A31, A32, A33. Just call it from A11.
1,
A22,
2, 5,
A33
9.
minus A11.
Ah, 8 to 2 is 2 now. Okay, no, fine. I don't miss.
A23 plus 6. A32 is 8, right? Right? I'm waiting for the answer.
Maybe 2. Yes, is it?
Minus A12.
A12 is 2.
A21.
4,
A33
9,
plus A12.
2,
A23
16,
A31
7,
plus
10,
okay, that's fine. Plus A13
3,
A21
5.
A32
8 1 we say what?
A21 say 5
It's 4 1 is 4.
A32
8 is 2 is 8.
minus A13
A1
A13 A22 A31
7.
so this will give me 45 minus 48 minus 72 minus 84. Sorry, this should be plus running. Plus 84. We are here now, right? We are here. 12 times 8, 96. Plus, right? Plus 96. 105. Minus 105. What should I do? Minus 105.
Chima.
What is it? Plus 8. 4 minus 500. 0. I got 0. Check if I'm correct. 2, 3, 4, 5. Who is that person? 5, 6, 7, 8, 9. So the next thing to do is to write plus, minus, plus, minus, plus, minus, plus, minus, plus. After that, you take 1 times this new matrix. So let's write that. So this is huh? I don't know that method.
It's not times that metric, it's times the altogether.
No.
No, when you say this times, that means it's like it's
Times the determinant of the matrix.
Yes, times the determinant of that metric.
Thank you.
Because
Determinant of this. So I have 1 times, because this is plus 1, so times determinant of 5, 6, 8, 9 minus 2. You are going to cancel this side and take the determinant of this and this. So we have 4, 6, 7, 9. Okay. And then finally, plus 3, right? So plus 3. Now, which sides would you close? You only close one directly under this 3. You are not going to use it. And then take the determinant of this. So you have times the determinant of 4, 5, 7, 8. The reason why we went ahead to write all these signs, you can decide to fix this rule and get the determinant using other rules. Depends on how simple. Like for example, if there are 0, 0 here, then it will be easy to use this rule to calculate the determinant, or even this column to calculate the determinant. So this is equal to 1, this times this, minus this times this. So let's do it. 5 times 9. 45 minus 6 times 8, 48 minus 2, 4 times 9, 36 minus 6 times 7, 42 plus 3 times 4 times 8, 32 minus 35. 7 times 5 is 35. So this is equal to 1 times this minus 3. This minus this is 6, right? Minus 6 plus 3 times 32 minus 35. 32 minus 35 is minus 3. So this will give me minus 3
12
plus 12 minus 9 equals to 0. Anyway, you feel like it's easier for you to use it.
Okay, ma'am.
So now we're going to do determinants of upper and lower triangular matrices. We need to know what upper and lower triangular matrices are. They are very simple to determine. If I have A to be equal to A11, A22, ANN. First of all, this is the matrix and this is the principal diagonal of the matrix. Right? We did it before. This is the principal diagonal of the matrix. If either all the elements here, all are 0 or all the elements here are 0, then we have an upper or a lower triangular matrix. So if all the elements up here are 0, then everything below that is a lower triangle. So this will become a lower triangular matrix. But if we have the other way around, we have that all here are 0, while all here there are other numbers, any other number, then what do you have? You have an upper triangular matrix. The whole of this upside will be an upper triangular matrix.
Okay,
If all the ones below it
are
are 0, then it will be upper triangular. If all the ones above it are 0, then it's lower triangular. Okay. So now, example. I'm going to write some matrices, then you tell me the type of matrix, whether it's upper triangular or lower triangular. Is this upper or lower triangular?
That's upper.
Thank you, because my triangle is up. What of? Is this upper or lower triangular?
No. Upper.
Upper. So this is an upper triangular matrix. Don't confuse yourself with the 0. What of? What kind of triangular matrix is this?
Like diagonal. I don't. I can't say upper. I can't say diagonal.
It's right now. Yeah.
It's both upper and lower.
Yeah.
It is both upper and lower.
So
Because when I draw the triangle like this,
The top of the inside. Okay.
everything on top of this is 0. If I choose to draw it the other way around,
Both upper.
yeah. So if I choose to draw it the other way around, everything under it is lower. So you see that this is a diagonal matrix. So when the matrix is both upper and lower triangular, we have the diagonal matrix. Now the aim of this is to find the determinant of an upper and lower triangular matrix. So remember that the determinant of A has the formula summation I is from 1 to n, right? The sign of the partition A1, P1, A2, P2, up to AN, PN. It is easy to see, but I want to help you to see that if I have, for example, let me write clearly. If I have a matrix A to be equal to A11, A22, up to ANN, and let's say that it's an upper triangular matrix, then every other thing here will be 0, right? Right? And then every other thing here will be other elements, any element is true. Let's say that this is AN1, A21. Now, if P1 here is 2, are you there? If P1 here is 2, we have A12, A12 is 0. If P2 here is 3, what we have is what? We have 0. In fact, anytime you have this thing having one element of this here, you have 0. So the only time that this formula will not have an element of the upper triangle, the upper part of the triangle of the matrix is if we have A11, A22, times ANN. Alright, so whether you have an upper triangular matrix or a lower triangular matrix or a diagonal matrix, the determinant is simply the product of elements of the principal diagonal matrix. Okay. We can go for next slide. Should we take examples? No need. Is there any need? If we have a 3 by 3 matrix, we have a 3 by 3 matrix. What kind of matrix is this? Lower triangular matrix. So what's the formula for finding determinant?
I'll use the circle. I'll use the circle. Copy John.
One into 6.
Six times are down here.
After is 6.
So it's 1 times 2 times 3. A11, A22, A33. Which is 6.
I didn't see that. To find the
So if I wanted to use that second method I taught of finding determinant, what I would have done is plus, minus, plus. I know that all here will be 0. So I would just have determinant of A is equal to 1 multiplying this determinant times determinant of 2013, which is 1 times 1 into bracket 2 times 3 minus 0 and which is 6. But this way is easier. Knowing that theorem is easier. If you like, you can go ahead and prove the theorem. Should I give you more examples or pass off? Let me give you pass off. Find the determinant of 1 IN 2 0 5 1 3. So down to this 3. You have 1 minute to be fast. This identity is an end-by-end identity matrix. So what's our answer?
1, 2, 0.
2 0. Very simple. So effect of exchanging rows and columns. So if I define A to be equals to A11, A12 up to A1n, A21, A22 up to A2n, up to AN1, up to AN2, up to ANN. Then, if I exchange maybe these 2 rows, any 2 rows, if I exchange any 2 rows to get a new matrix AB, then determinant of B is equal to minus determinant of A. Do you understand?
Yes.
So for example, if I have A is equal to 1 0 0 1, this is identity matrix, right? Then the determinant, and I say B is equal to, I exchange these 2 rows, I have 0 1 1 0. Then determinant of B is equal to minus determinant of A. So what's determinant of B? First of all, what's determinant of B?
1.
So what's determinant of B?
0.
Ah! I need determinant of B is equal to minus determinant of A.
It's minus 1.
So if I extend 2 rows, maybe this is, if I have I row and I have here the j row. If I extend the I row and the j row to get a new matrix, then determinant of B must be equal to determinant of B, where B is the new matrix. Now, if this is one swap, I swapped once, I swapped 2 rows once. If I swap again, what will happen? What do you think will happen?
Plus.
It becomes plus because it's minus determinant of A. If I swap again, it becomes minus. So if you swap odd times, you have minus determinant of A. If you swap even times, you have determinant of it, then determinant cycle. Okay? So the next. We are going to check the effect when I multiply A by some constant. So if I multiply a rule here, maybe let me call this AI1, AI2 up to AIN. If I multiply this rule by some alpha, say this is alpha times alpha, everything in this row is multiplied by alpha, then I got a new matrix B. Then we have the determinant of B is equals to alpha times the determinant of B. Is it okay? So what do you think if I multiply the whole matrix A with alpha to get B? What will the determinant of B be? You know, if you multiply A with alpha, then you have alpha multiplying this row, alpha multiplying this row, alpha multiplying this row, alpha. So what do you think will give you? What do you think your determinant of B will be? Alpha determinant of B. Any other person?
Alpha is power n.
Determinant of A. Any other person? Let's go. Which one do you think is correct? If you go for the first option, raise up your hand. You know, you are not going for what you chose. So this is the correct answer. So if I multiply the first one row with alpha, I have alpha determinant of A. If I multiply another row, I have alpha squared determinant of A. If I multiply another row, all through, let me put it outside. Alpha, multiplying all through again by alpha. Multiply all the n rows by alpha, then this will be alpha raised to power n determinant of alpha. So that's how it goes. So this is wrong. So here it says this is the first one, first effect. The second effect says multiplying one row or one column by a scalar alpha. Then you have determinant, then you have multiplying one row or column of A by a scalar to give us B. To get B means that we have that determinant of B is equals to alpha determinant of A. The last one is said that if you have alpha times A is equals to B, it implies that determinant of B is equal to alpha determinant, alpha raised to power n determinant of A. Do you understand?
Yes.
So if I have A is equal to A11, A12, up to A1n, and I have some I row to be AI1, AI2, up to AIN. And then I have, continue going, I have another row, maybe the J row, this is the I row. But the J row is still AI1, AI2, up to AIN. And then I have up to AN1, up to AN2, up to ANN. Then what this means is that, if I have two rows that are exactly the same in a matrix, two rows that are exactly the same, then the determinant of this matrix is 0. The determinant of A is equal to 0. Can we prove it? We are going to use what we have here to prove it. So let B be a matrix such that the I2, this is the I2, right? And the J2 are exchanged. What will happen? According to this, what does it mean? Determinant of B is equal to minus determinant of A. Is it not? But A is exactly B. Why? Because the J2 is I and this is AI. So if I swap them, I still have the same thing happening. but B is equal to A. So that means that determinant of A is equal to minus determinant of A. What does it mean? It means that 2 determinant of A is equal to 0. If I divide both sides by 2, I have determinant of A must be 0. Do you understand? You don't understand? I'm going to give an example. Okay, let's take an example so you understand. So if I have a matrix 1, 2, 1, 2, I'm claiming that the determinant of this matrix is 0. With this theorem, I can just say determinant is 0. But if you want to use your hand, then determinant of A is equal to this times this, 2 times 1, right? Minus this times this, 2 times 1. What would I give you? 0. It is not the same thing as saying A is equals to 1, 2, 2, 1. It's not the same thing. These two rows are not identical, these two columns are not identical. So I can't say that. Neither the rows nor the columns are identical. I'll get a different number. We should take, right? Let's call this A2. So determinant of A2 will give me what? 1 times 1 minus 2 times 2. That's 1 minus 2 minus 2. So be careful. So let's take the following exercises. You can pause your video and try out all these exercises and see if you can apply what we just learned about the effect of exchanging rows and columns, multiplying a row by a scalar, or multiplying a column by a scalar, or exchanging rows or columns, and so on. All we just learned previously. Let's go. At this point, we should be done. Are we all done? Are we all done?
Yes.
Okay. So let's say the answer. What's the answer? 0. Why? Why? Nobody. But you know it's 0. This column and this column are exactly the same. So it's 0. When you have identical rows or identical columns, you get 0. The next one, what of this? 5. So what we did, this is an upper triangular matrix. So this is 0, so we have to multiply just this 2. And we get 5 times 1, which is 5. What is the determinant of this? 0. 0. Why? Okay, if you observe, this looks like the identity matrix. You just need to swap this and this. That's one swap. So you have this one here, right? But it's not supposed to be here, it's supposed to be down here. So you swap again. That's 2 swaps. So the number of swaps is even. That means the determinant of A is the determinant of C because the determinant of the identity matrix is equal to 1. Okay, well, next one. It says suppose A is this and the determinant of A is 3. Then find the determinant of this. What did they do here? Now this second row is minus 7 times this row. Right? Is it not? So the determinant of this is minus 7, determinant of 8, which is 3. And that is minus 21. The next one, they swapped the 2 rows. So determinant of C is minus determinant of A. This implies that determinant of C is equal to minus 3. What of this one? They multiplied the whole matrix, if you observe, by 2. Right? So I need to multiply by determinant of A by 2 raised to power 2, because this is an A 2 by 2 matrix. 2 raised to power 2, determinant of A. That's 4 times 3, which is 12. The next one, what did they do? They multiplied this matrix by 4 and then swapped the 2 rows. Have you seen it? If I multiply this matrix by 4, I'll have 28, 4, 4. Then they swap the two rows. So, but what's the determinant of this matrix? 4 raised to power 2, determinant of A, that's times 3. 4 raised to power 2 is 16 times 3, which is 48. Now, here, they swap these two rows. So the determinant of this should be minus the determinant of this matrix, which is equal to minus the determinant of 48. Minus the determinant of this is minus 48. And then finally, the determinant of this is simply what they did, they multiplied this whole matrix by minus 1. Right? So this is minus A. This is equal to, this implies that the determinant of F is equal to determinant of minus A, which is equal to minus 1 raised to power 2 times 3, which is equal to 3. Okay, that will be all for today. Thank you for coming around and thank you for watching. Please like the video and subscribe to the channel. Bye!